So now that we've talked about intermolecular forces, you guys, like we spent a whole chapter talking about IMFs. I want you to start thinking about IMFs all the time, like with all of our other topics that we talk about. I want you to be thinking about things on the particle level and be thinking about the interactions that are taking place there. Okay, no problem, Sam. Oh my gosh, people are popping in and popping out, popping in, popping out. Can you guys hear me okay? Okay. All right. So first thing I want you guys to think about is when we have a solute going to dissolve in a solvent, one of the things that has to happen is the attractions of the solute particles to each other have to be sort of overcome, right? Because a solute has its own IMF that's present. And we call those solute-solute interactions, right? Because like if this is ionic, it would be a crystal lattice. If it was a polar substance, it would be a dipole-dipole force. Those interactions have to be overcome. The other thing that has to happen is the attractions between the solvent particles also have to be overcome, right? Like, so if this is water, there's these hydrogen bonds between the water molecules. But what's cool about dissolving a solute into a solvent, so like if this thing is soluble and we make a solution out of it, we're going to end up with some solute to solvent attractions. And if these attractions are strong enough, then we're going to get a nice stable solution. Like we're going to get this solute able to dissolve in the solvent. That's why we have that rule, you guys, for like dissolves like. In other words, the solute has to have similar IMFs to the solvent in order to have these solute-solvent interactions. Okay, no problem. Thank you. All right. Also, for those of you that are having trouble with the audio today or bumping in and out or you're doing multiple things at once, I'm recording. So I'll post the recording later for you guys. Okay. So I want you to start thinking about these things in terms of energy as well. So in order to overcome the solute-solute interaction, that would be an energy input. Like I would have to put energy in order to separate the IMFs of the solute to the solute. I would also need to put energy in order to separate the IMFs of the solvent to the solvent. Right? Like if I wanted to separate the hydrogen bonds that are holding the water molecules together, that would be an energy input as well. So you can see these first two parts of the process are endothermic. You have to put energy in to break apart those IMFs. But the reason why substances go into solution is because like dissolves like, and there's going to be an IMF between the solute and the solvent. That's going to always release energy because an attraction provides stability. So the solute attraction to the solvent is going to release energy. So notice I went in the other direction. Depending on how much energy gets released, you might have a positive delta H for this process. You might have a negative. So this is my energy. This is my final position. This is where I ended up. And this is my initial position, how much energy I started with. Final minus initial, this is going to be a positive delta H of solution. Like I had to put more energy into the process than I got out of it when the solute and the solvent attracted to each other. So if the solute-solvent attractions are not very strong and you don't get like a big release of energy when these two things attract, this is going to be an endothermic process. But if you dissolve a solute in a solvent, that really, really want to dissolve in one another, like there's a very, very strong attraction between the solute and the solvent, and you get like a really big output of energy. Like let's say my initial position, this was my initial position like it was before, but my final position is down here now. I ended up releasing energy. This is a negative delta H of solution. This would be an exothermic process. So some things, when they go into solution endothermically, and other things go into solution exothermically. So some salts you dissolve and they feel cold because you had to absorb energy from the water in order for that salt to dissolve. And sometimes they release energy and they feel hot, like hot packs and cold packs, you guys. You know, when you like break the little packet and you shake it, you're making that salt dissolve in water. So hot packs and cold packs are made with different salts, some that have positive heats of solution and some that have negative heats of solution. Either they are endothermic or they are exothermic. Any questions there? Now, something else happens besides a change in heat when a solute dissolves in a solvent. Anytime you make a solution, oops, I did not want to be in blue there. Anytime you make a solution, you increase the entropy of that system. You get an increase in entropy, not enthalpy, entropy. Entropy is a word we have not yet learned. We're going to spend a whole chapter talking about entropy. Entropy is like the messiness or the disorder of a system. When a solid or liquid dissolves into solution. Now, it's not the case for when gases dissolve. Gases, you can dissolve gases in solution, but it actually is more ordered because gases are very disordered. They're very messy. They're very far apart. They have lots of different possible positions. You can think about disorder as possible positions, possible interactions. Like if I've got all the girls on one side of the room and all the boys on the other side of the room, the girls can only interact with the girls and the boys can only interact with the boys. That's a pretty ordered situation. But if I mix you guys all up, you can have girls interacting with girls, boys interacting with boys, girls interacting with boys. Like there's a lot more options for interactions when you mix up those two groups of people. So it's the same thing with solutes and solvents. Okay, you get more disorder when you dissolve solids or liquids into solution. And this is favorable, meaning it makes this more likely to happen. Like, so even though some solutions are endothermic and require an energy input in order to get them to happen, you're like, well, why would it happen if it needs an energy input? Well, because even with that little bit of energy input, it is still a favorable situation to have more disorder. The universe is tending towards disorder. The universe is expanding. Things become messier and more disordered as time goes on. It takes energy to keep things orderly. That's why your rooms are always a mess, right? Because like it would take energy to keep your room neat. Okay, so the reason we're talking about entropy here is because it's going to play a role in some other things that we're going to talk about a little bit later on. Any questions so far on any of this vocab? Okay, so now let's talk solubility. Like this process that I just talked about is the solvation process. Solubility is a actual measurement of how much solid or liquid or gas, how much solute can dissolve in a given amount of solvent at a particular temperature and pressure. Okay, so temperature and pressure both matter here. So, like, for example, I could say that the solubility of, I'm literally making this up, sodium chloride. Like, let's say the solubility of sodium chloride is 10.0 grams of NaCl in 100 milliliters of water. I don't know if that's the solubility of sodium chloride. I think it's probably not. You can probably dissolve a lot more than that. But that would be an example. This is how much of the salt can dissolve in a certain amount of solvent at a particular temperature. Pressure, whenever we're referring to like the normal solubility of something, it would be 1 atmosphere of pressure. In other words, temperature and pressure will affect how much of this stuff you can dissolve. If you increase the temperature, you get an increase in the solubility of solids and liquids. This is not true for gases. If you increase the temperature, you actually decrease the solubility of gases. And if you think about it, it makes sense, right? When you increase the temperature, you make the water move faster and farther apart. Like, you make more room for more solute, solid or liquid, to dissolve. But remember, gases, we did like a whole chapter on gas laws because gases behave totally differently than solids and liquids. Gases do not want to be dissolved at all. Gases would rather be out of solution. There's more disorder for gases out of solution than in solution, because when they are out of solution, they can be really, really far spread apart. To get gases to go into solution, you need pressure. You actually have to like push a gas to get it to go into the aqueous state. Okay. So if you were to increase the temperature of your water, you're now encouraging those gas particles, right? With an increase in temperature, gas particles expand. So you're going to make those gas particles expand right out of solution. Okay, so an increase in temperature is not helpful in terms of affecting the solubility of a gas. It makes them less soluble. So in fact, gases need a pressure exerted above the solution in order to dissolve. So like, think about this. Like, if this is our soda can here, right? And here's like our sugar water. In order to get that carbon dioxide into solution down in here, to get CO2 aqueous, we need some CO2 particles up in here, right? We need some pressure exerted by CO2 particles up top. If I were to open this can and release that pressure, these bubbles of CO2 down in here are going to leave solution. In fact, how much CO2 is dissolved in the liquid depends upon how much pressure there is up above the solution. We can actually write an equation for it. The solubility of the gas is equal to a constant times the pressure of that gas above the solution. In other words, they're directly proportional. The more pressure you have above the gas, the more soluble that gas is, right? With an increase in pressure, you're going to get an increase in solubility. And the reverse is also true. If you were to pop that can open, you would get a decrease in pressure and thus a decrease in the solubility, and the gas would bubble out. Don't worry about what the constant is. You'd have to look it up for different solvents and different solutes, like which gases you're dissolving. So don't worry about that constant. We're going to just talk about this more qualitatively. And this is called Henry's law. Which basically says that the solubility of a gas is directly proportional to the vapor pressure of that gas above the solution. Okay, so I just told you that solubility is like this maximum amount that can dissolve. Like I made up an example that like the maximum amount of sodium chloride you can dissolve at 25 in 100 is 10 grams. I made that up. But let's stick with that as our example. So let's go ahead and let's draw 3 beakers here. I'm going to demo this for you guys tomorrow in school because it's pretty fun. All right, so let's say we have 3 beakers, all with 100 mils of water. And we'll say that they're all at 25 degrees Celsius and 1 atmosphere of pressure. So we know, based on what I set up here, that the maximum amount of solute that you can dissolve is 10 grams. All right, well, let's say I dissolve 6 grams. If I have less than the maximum amount dissolved, we call this solution unsaturated. If I were to dissolve 10 grams, 10 grams, 1, 2, 3, 4, 5, 6, 7, 8, 10 grams, all dissolved. This would be a saturated solution. Now, what I want you guys to recognize is that it doesn't have to be exactly 10. Like if I dumped in here like 13 grams, let's say, 10 of it would be dissolved and 3 of it would be sitting down here undissolved as like a precipitate. Okay, this would still be a saturated solution, right? Like no more than the 10 grams that can dissolve at this temperature is going to dissolve. Okay, so you're going to have saturated solutions where you don't see any precipitate because like let's say you got just the right amount, the maximum amount with no leftover. But more often than not, when you have a saturated solution, you actually usually do have precipitate down here at the bottom that was unable to dissolve. That does not make it supersaturated, right? Your maximum amount is your maximum amount, and the fact that you have some left over down here at the bottom just kind of goes to prove that we dissolved all of it that we could dissolve, okay? So saturated is when you have the max amount of solute dissolved. Unsaturated is obviously when you have less than the max amount of solute dissolved. And if we're going to go to something called supersaturated, that must mean that you have more than the max amount dissolved. And hopefully you're like, how do you have more than the max? Like the max is the max, right? And I told you that just like having a bunch of precipitate down here at the bottom doesn't make you supersaturated. That's still just saturated. The way that we get to a supersaturated solution is we take a saturated solution and we heat it, right? Because remember, this is saturated at 25 degrees Celsius. But if I take that 25 degrees Celsius and I heat it up to like 30 degrees Celsius, now you can get more than the maximum to dissolve, right? So like maybe now I can get like 20 grams of it to dissolve. I'm not going to count. I was trying to make each dot represent a gram, but who cares, right? If I heat this, I can get more than the maximum amount to dissolve. But then you have to cool it back down to 25 degrees Celsius because the 20 grams is how much can dissolve at 30. That wouldn't be supersaturated. That would be saturated at 30 degrees Celsius. And then you gently cool it back down to 25. So like you separate out the water molecules, you dump a bunch more solute in, you gently cool it down, and it'll stay dissolved, which is kind of cool. Because if you were to then like agitate the solution, like bump into it or pour it or cool it too quickly, all of that solid will all come crashing out at once, which is kind of a fun thing to see. And so we'll do that in class tomorrow, where we take a supersaturated solution and we disturb it. And you'll see all of that precipitate like come out at once. You can think about supersaturated like you go to the carnival and you just eat a bunch of junk food. You have like the corn dog and the popcorn and the fried dough, and you're like so stuffed. And then like you go on a ride and you puke, right? So it's kind of like the same thing with a supersaturated solution. They're very unstable. Supersaturated solutions are also how you make like rock candy. You make a supersaturated sugar solution and then you stick a stick in it. And as it cools and the water evaporates out, that supersaturated sugar crystallizes out on that stick. So there's some sort of real world uses to supersaturated solutions. Any questions there? All right, this is section, I think it's section 13.5. And it's called, I love this word, colligative properties. Now, this particular portion of the chapter is not on the AP exam, but we're going to talk about it anyway. One, because there's some real world uses for it. So like sort of just in terms of understanding the world around you, it's kind of important. Two, big part of college chemistry. So I don't know why they scrapped it from the AP exam, but so not important for the AP exam, but yes, important for college and for life. Colligative properties are properties of a solvent that change depending upon how much solute is dissolved. Now I highlighted how much solute is dissolved because that's the only factor that matters. The identity of the solute does not matter. Like it doesn't matter if it's sugar or if it's salt. It doesn't matter what the thing is that you're dissolving. It only matters how much of it you dissolve. So independent of solute identity. So these are things about solvents that change when they become a solution, in other words. Okay. The first one, the first thing that changes is vapor pressure. let's review what the heck vapor pressure even is, right? Let's draw ourselves a diagram. I have a beaker, or a closed container, I should say. Closed container is a better thing to consider here. And I have a liquid down here. So like, let's say this is water, H2O. I'm going to have some of it down here in the liquid phase, and I'm going to have some of it that became a gas. This pressure up here, this normal vapor pressure of the solvent, that's the vapor pressure. And I don't know what the vapor pressure of water is at 25. I'm going to guess. Let's say it's 17.5 torr. That would be the normal vapor pressure of water at 25 degrees Celsius. That's just naturally how much of this liquid goes up into the gas phase through evaporation, right? Remember, they're going up into the gas phase and condensing back down into the liquid phase. And however much pressure is up here at any given time, because it's at equilibrium, that's your vapor pressure. Okay. Now here's the thing. When you dissolve anything in this liquid, so like let's say, back to our example up above, let's say I dissolve 10 grams of NaCl in this 100 grams of water, okay? If I dissolve the salt into the water, something's going to happen to this vapor pressure. It's going to go down. This is called vapor pressure lowering. Solvents have less vapor pressure when solutes are dissolved. To become solutions. And here's why. Remember we were talking about solute-solvent interactions, right? Like if I dissolve sodium chloride into water, I now have, in this case, ion dipole, solute, solvent attractions. It used to be that the water molecules were just attracted to each other, and that, you know, sort of prevented them from becoming a gas. So you had pretty low vapor pressure. But now, in addition to there being the hydrogen bonds between the water molecules, now the water molecules are also attracted to the ions of the salt, making it even less likely for the liquid to become a gas, right? So you have these new solute-solvent attractions and more entropy, right? We've made this more disordered. By dissolving a solid into this liquid, we've increased the disorder, and that's favorable. It's less likely now for the water to have to become a gas to become messy. It's already messy. We dissolved a bunch of salt into that solution. So with that increase in entropy and those solute-solvent attractions that we didn't have before, we now have fewer particles in the gas phase. We have lower vapor pressure. So now maybe we only have like, I don't know, 16 torr of pressure. But we can actually calculate it, okay? And the calculation looks like this. The vapor pressure of the new solution, right? The vapor pressure of the solution, once we've dissolved the solute, is equal to the mole fraction of the solvent. Remember, X is mole fraction. That was one of the things we calculated for last week, times the normal vapor pressure of the solvent. And this is called Raoult's law. So let's calculate it, right? Let's calculate what the vapor pressure would be now. Like I told you, it was 17.5 torr before we dissolved the salt. But once we dissolve the salt, let's see how much that vapor pressure goes down by. So what we need is the mole fraction of the solvent. Okay, so I need to turn my solute into moles, and I need to turn my solvent into moles. So 10 grams of sodium chloride, molar mass is 58.5 grams. And I've got 100 grams of water. Molar mass is 18 grams. Okay, so my mole fraction of my solvent is moles of solvent on the top, 5.56, over my solvent plus my solute. Okay, so this right here, you guys, is my mole fraction, and moles over moles, it'll be unitless. That's the mole fraction of my solvent, times what my normal vapor pressure is, so 17.5 torr. And so my new vapor pressure, it would help if I turn my pen the right way. My new vapor pressure is 16.98 torr. See how it went down, right? We started off at 17.5 torr, and now it's down to 16.9 torr. So you take a little bit of solute, you increase the solute-solvent interactions, you've increased entropy, it is less likely for that liquid to become a gas. This next one is related to vapor pressure lowering. If you recall, a substance boils when the vapor pressure is greater than the atmospheric pressure pushing down on it, right? So when we add enough heat to get that vapor pressure big enough to overcome the pressure of the atmosphere pushing down on that liquid, that's when something boils. But if we've just lowered the vapor pressure, if by taking a solute and we've made it less likely that the liquid becomes a gas, we've now made it harder to boil it, right? If we've lowered the vapor pressure, we've now increased how much heat we need to give that substance to get that vapor pressure high enough to boil it. This is called boiling point elevation. This is our next colligative property. Okay, so with less vapor pressure, and more solute, solvent interactions, and entropy, the solvent is now harder to boil. In other words, it needs more energy. So water that would normally boil, so like the normal boiling point of water is 100 degrees Celsius. It's going to go up from there. So, you know, if you were under the misconception that putting salt into your pasta water makes it boil faster, you're wrong, okay? It doesn't. Putting salt into your pasta water seasons your pasta. It does not make your water boil faster. In fact, it's going to take longer to get your water to boil because now it's not going to boil at 100. It's going to boil at like 105, depending on how much salt you put into your water. And again, it wouldn't matter if you put salt in or if you put sugar in. Putting any solute that is soluble into your solvent increases its boiling point because you've lowered the vapor pressure. You've now made it harder to become a gas. And so the boiling point goes up. And we can calculate it. And the equation looks like this. I love this equation. I don't know why. The change in the boiling point is equal to I KB molality. You're saying that as I eat my pasta, don't you? It's not wrong to put salt in your water, right? It's not wrong. Oh, sorry, I was reading a chat. It's not wrong to put salt in your water. It makes your pasta tasty, but it's just going to take a little bit longer to get your water boiling. But maybe your pasta probably cooks a little bit faster though, because once you put your pasta in, that water is at a higher temperature than it would be if you your visual cue to put the pasta in is boiling water. And if you didn't put any salt in, that water is at 100 when you put your pasta in. If you had put salt in and then you put your pasta in when it boils, it's now at like 105 degrees. So the water is hotter when it's boiling. So maybe your pasta cooks faster. So it's not wrong. In fact, it's delicious. All right, anyway, sorry, I got sidetracked. Here's our equation. The delta T BP is the change in the boiling point. Right, so this is the change. So this is what you would add to 100 or whatever your normal boiling point is, depending on what your solvent is. Our solvent is always going to be water. This M is for molality. And remember I said we use molality instead of molarity when we're working with changes in temperature because molarity will change with changes in temperature. So this is why we use molality, which you remember is moles per kilogram, right? Moles of solute per kilogram of solvent. KB is a constant. Again, different for every solvent. The KB for water is 0.51 degrees C per molality. And this I here is called a Van't Hoff factor. Fancy name for a simple thing. It represents the number of ions dissolved. Here's the thing with molality, you guys. If I calculate the molality of NaCl, which was the solute we've been talking about all day, it does not take into account the fact that when NaCl goes into solution, it breaks apart into Na plus and Cl minus. So if I calculated like a molality of 2 molal, it is not taking into account the fact that I'm actually going to get 4. I'm going to get 2 times 2 dissolved particles because for every one of these that dissolves, I'm going to get 2 ions. So this Van't Hoff factor accounts for that. So the I for NaCl would be equal to 2, right? Because for every one of these, I get 2 dissolved ions. If my salt was MgCl2, I would get magnesium and I would get 2 chloride ions. Here, my I would be equal to 3, okay? It's a multiple that allows us to increase our molality to account for the fact that when 1 unit of this dissolves, I'm actually getting multiple particles dissolved, because it's not about the identity of the particles that's dissolved. It's only about how many or how much stuff is dissolved. If your solute is covalent, like glucose or something, those do not break apart into ions, right? Covalent particles do not dissociate. So it's a 1-to-1, right? Your molality is accurate. You do not need a Van Hoff factor. Your Van Hoff factor for covalent would just be 1. Because for every one of these that dissolves, you get 1 molecule in solution. But for ionic, you do have these values. Now, these are actually maximum values. And when you go to college, like, you'll recognize that at different temperatures, these values can go down a little bit. Like, not every single unit of the salt dissociates. So really the Van Hoff factor will be something like 1.8 instead of a 2. But again, that's like a complexity that we don't need to exactly worry about just yet. Okay. So if I wanted to calculate the change in the boiling point, back to the example that we did up above, what would be the change in the boiling point if we dissolved that 10 grams of salt, like we did up here, and this 10 grams of the sodium chloride and the 100 grams of water? My Van Hoff factor for sodium chloride, like I said, is 2. I get 1 sodium ion and 1 chloride ion. My boiling point elevation constant is 0.51 degrees C per molality. And now I just need the molality of the solution. And if you guys recall, right, it was 10 grams of NaCl. Oh, I don't even need to do this. I already did this. Do we have moles of NaCl? Yeah, here it is. 0.171 moles of NaCl. 0.171 moles per kilogram of solvent. And so we had 100 grams of water. So 0.100 kilograms of solvent. You don't even have to do any extra work. Okay, and this will tell me how much my boiling point will go up. 2 times 0.51. 71. My boiling point is going to go up by 1.74 degrees Celsius. If you're bothered by the units here, remember this is molality. Moles per kilogram is molality, right? Like that's what moles per kilogram means. So the molalities will cancel and you'll be left with degrees Celsius. So instead of boiling at 100 degrees Celsius, you put that salt, if you put 10 grams of salt in your pasta water, now it's boiling at 101.74 degrees Celsius. Any questions there? All right. I think you've got one more in you. In addition to making solvents harder to boil, we've also made them harder to freeze, right? Because if you think about it this way, if you've got a bunch of stuff dissolved in your solvent, it is going to be harder for it to solidify because there's like solute particles in the way. So going from a liquid to a solid is a decrease in entropy. Like we're making it more ordered when we're trying to put it in the solid state. But if we've already made it really, really messy by dissolving a bunch of solid in it, it's going to be even harder to get that stuff to freeze. This is called freezing point depression. And there's a really good real-world example for this as well. Sort of more important than your salty pasta. Freezing point depression. Dissolving a solute in a solvent increases its entropy. We already talked about that. And makes it harder to freeze. More energy must be removed. You can think about it as in these solute particles are in the way of the solvent coming together and crystallizing. I think that's sort of the easiest way to think about it. Or you can think about it in terms of entropy. Like it's really messy. You've increased entropy by dissolving the solid into the liquid. It is now less likely or harder for it to become more ordered and go from the liquid state to the solid state. Okay, so instead of freezing at like 0 degrees Celsius, it now has to be like, I don't know, negative something, like -5 degrees Celsius maybe. This is why we salt our roads in the wintertime. So if you think about it, if there's no salt on the roads, right? If you've just got water on your roads, as soon as the temperature hits 0 degrees Celsius, that liquid is going to turn to solid. It's going to be icy. Roads are going to be slick. But if you dump a bunch of salt onto those roads, now it needs to be -5 degrees Celsius in order for that water to freeze. So if it's not -5 degrees Celsius outside, that ice on the road is going to melt, okay? Because you've lowered the freezing point. And the good news is the equation is the same. Delta T of our freezing point is equal to I KF times molality. So like I just made up that it would drop to -5. I don't know what it would drop to. I didn't calculate it. Everything is the same except for your KF. The freezing point depression constant for water is 1.86 degrees C per molality. So we could calculate it. Like I guessed -5. That's probably not right, but whatever. You can plug and chug. If we're using the same example from above, my molality was 0.171 over 0.1 molal. Ooh, it was more than that. It's 6.36 degrees Celsius. So I didn't drop it to -5, I dropped it to -6.36 degrees Celsius. So the next time your parents ask you to go de-ice your steps, now you know the chemistry as to how that works. Okay. There's one more colligative property, but we'll save that for tomorrow.